to be looking into the second Foundations of Physics practical assignment, focusing on Newton's law of gravitation. I completed this prac with my lab partner, Tilly Druce. Firstly, we'll look into some physics principles, mainly Newton's law of gravitation, as this was the focus of the prac. This law states that every particle in the universe attracts every other particle in the universe, with a force proportional to the mass of each particle. This can be calculated using the formula displayed here. Force is equal to G times mass 1 times mass 2 over r squared, where G is the gravitational constant, 6.67 times 10 to the negative 11, and r is the distance between the two particles. This can then be used to calculate the gravitational force between any two objects. Next, let's get into the objective of this lab, which was to measure the acceleration of gravity, or g, using the equipment available to us. We decided on using a pendulum test, a simple way to measure this acceleration. This test is built around the idea that when the amplitude of the oscillation is small, or less than 10 degrees, the oscillations are harmonic, giving more reliable data. It utilizes a pendulum which is made up of a length of string, or similar, secured to a fixed point on one end and a mass on the other. You then drop this from an angle of less than 10 degrees and record the time it takes to complete one oscillation back to the starting point. You can then use this data in combination with the formula T equals 2 pi square root length over gravity rearranged to find our acceleration. The rearranged equation is length over brackets time over 2 pi brackets squared is equal to gravity. We then use this theory to complete our own calculations. So, let's get into the experiment itself. We set up our own pendulum, shown below, with a length of 0.35 meters and a weight of 200 grams. We then dropped the pendulum from an angle of 10 degrees. This was a mistake in our experiment, as to achieve harmonic oscillation, it should be less than 10 degrees. We recorded the time that it took our pendulum to complete one oscillation, and repeated this 10 times, as shown on screen. I'll skip over the whole video, but I'll speak about my measurement uncertainties while some of it plays. In our experiment, we had a number of relatively minor measurement uncertainties that were likely to affect our final results. Most of these were just human error that happens without special calculated devices such as motion trackers. We would have encountered error in our recording of the oscillation time due to human clumsiness and very small amounts of time. The other human error to consider would be the change of drop angle by minor amounts each time, leading to slightly more variation. Lastly, I believe that the vertical plane that the drop is intended for could be deviated from, affecting the exact measurements. Now, let's look at some results we achieved. Displayed here is a table of all the times we recorded. You can see the variations in time that can be described by our measurement uncertainties. We had a range from 1.03 seconds in trial 9 up to 1.33 seconds on trial 2. We then averaged the results and calculated the uncertainty as shown here, using the formula Vmax minus Vmin over n, or your maximum value minus your minimum value divided by the number of trials you completed. This gives us an uncertainty of plus minus 0.036 as shown below. At last, we can get into the calculations for the acceleration of gravity given by our aforementioned formula. We subbed in our values 0.35 over brackets 1.233 over 2 pi brackets squared is equal to 9.088697058 meters per second squared. This varies slightly from the accepted value of 9.8 meters per second squared, which would likely be due to our uncertainty measurements. Thanks for listening. Thank you.